Hey everyone, how's it going? We're back here with another Facebook Hacker Cup. This is the 2022 qualification round. I guess they're calling it Meta Hacker Cup now, but same thing. Let's get started. I think I'm going to actually go for B because there's two parts, so helps with the penalty. Do not contain rocks. Okay. This means there's already a tree. Okay. Okay, so this one, B1 is actually, so as long as, if either dimension is 1, it has to be empty. Otherwise, you're always possible. Okay, and then oh, sorry, has tree. Grid RC equals this. This has tree. We can just start here actually. This would be impossible. Turn. Otherwise it's possible, and if has tree, then we're just going to fill it out with trees. Some assignments, and then possible. Yep, looks good. All right, here we go. Validate. Cool. Password protected, but then I think there was a way to just get the full input. Yes, here. I'm just gonna do this. All right. Cool. Looks like that worked. Let's submit it. And then for B2, if there are rocks, how do we handle that? This actually is fairly different. Maybe I should just do A. Two cases that can hold K parts. Neither two different parts of the same style. Okay, so for each style, I see. So here for each style, if do you need to do it? No, you don't need to do it. Okay, so if that second is greater than 2, and now if there's 2 is equals 0, 1 is equals 0. So we're just going to do this, essentially. Twos plus 1. It's at most k, right? So I think that's what it is. Alright, A. Let's just, I guess that's good. You're gonna make it difficult for me with these. Oh no! Oh no! They're all gonna start with the second. It's because of second thread. Oh, that's the worst. That is the worst. All of these files are gonna give me trouble. Second hand txt, yes. And output txt looks good. Source code, right? Yes. Now, if there are rocks, what do you do? I don't know that it's super easy. I would have to think about this one. Try to figure out this strategy here. Got A, got B1. B2 if there are rocks. I think you have to peel all of the... This only has one neighbor, remove it. Yeah, I think I know what to do. I don't know if this is the fastest thing to code. Maybe C1. Let's take a look. I see. Yeah, they're all called second. Oh, unambiguous. Oh, you're just building a prefix-free encoding. Wait, don't I have... Just make them all length 10. Make them start something different, and then... I think I can solve this. So, yeah. It should just be prefix free. The way you do that is... You're just given one... Yeah. Okay, and then n is, I think it has to be at least 2. So basically, we're gonna say dash and dot. And then we're going to get... Alright, and now what we're going to do is string, so I have when, string 0 is going to be opposite C0. String plus equals I bit in 1. Is this right? I think, yeah, let's just try it. The validation will help a lot here, actually. That looks like it works. All right, let's do it. Let's do this. And let's do this. Okay, cool. Let's do this too. Oh, this is the worst. Cool, let's do it. I should automate this somehow. All right, anyway, should be good to go there. Cool. That is problem C. All right, now we have B2 and D remaining. B2 is probably better than before. So what I want to do is I basically want to peel leaves. Anything that has a degree of 1. Just repeatedly peel those. If I try to peel an existing tree, then that is a fail. I think that is what we're going for here. We don't need E. It's going to be saved as B1, and now, yeah, we're going to do this. How are rocks represented? This is rock. Okay. You're kind of building a graph, right? If grid RC is not equal to rock. If it's not a rock, then we need to, yeah, we need to add it to the graph. All right, and now we're gonna do, sure, we're gonna do this. Grab BFS, grab this, grab that. Grab bool. Check if we're inbounds, and then we're gonna go in the 4 directions. This is also not a rock, then we're going to add edge. I guess I only want to do this. Yeah, I actually only need to do this. So I don't need this, get rid of this. Okay, that is our adjacency graph. Now we're going to peel it. What does that mean? That means while we're going to do a Q, we're going to have a degree. All right, and now, while not, oh, we don't need to do this. We don't need to do this at all. Okay. If you have a tree and the degree of bit index RC is less than 2, then you failed. Then you failed, and then you see out impossible, and then you return. Otherwise you see out possible, and then you just go through here. If degree get SC is equal to 2, set to tree, and then do that. Yes, I think that is what we want. Impossible, possible. Okay. Let me try one more case where we have a bunch of. I want 5, actually. That's actually not what I wanted. Oh, that's fine then. Let's do it. Second friend. I'm actually so mad at second third for these names. Let's do it. Let's do the full thing. Let's do it. I probably don't have the time to do that. This is b.tc. Yes. Alright, we have one left. Let's do it. Complete down the compressed. Cool, what are we doing here? Flight I can text AI and BI in both directions. 2 flights go every morning, another 2 every evening. Each of these flights carries CI tourists. Oh, okay. Okay. From airport XI to Y. For each day. Oh, it's okay. It's just a query problem. Nothing actually changes. It's just from a xi. So you can take 2 flights at most. And the constraints are kind of huge. Sitting at first looks like a good lead right now. Okay. They don't have a constraint on the sum of n and m. Seems bad, but anyway. AI, BI, CI. Yes. Okay. I have submitted, right? Wait, have I not submitted? What happened? What is happening? It says I have not made any submissions? Didn't I do this? No, confused. Okay. Just gotta solve this. So what is that? Oh, is that what happened? Second friend output. b.cc. I need to submit communication for this. What is wrong? Should I download it again? It's the same. Second frame output. b.cc. This is why you don't name your problems like this. Am I? No one has been able to successfully solve this problem, so it's not just me. Okay, it's not just me. It's not just me. I'll just keep going. Okay, so really, what we're doing x and y, right? So first we have the direct x and y, which counts twice, I think. Okay, yeah, so we're just querying my timer expired. Okay, well, they need to fix that, but in the meantime, yeah, I think you can just cache each XY query, and then you just iterate over the minimum of X's and Y's. Yes, yes, that, I think that's it. This is a square root. So in that case, we're going to have okay, let's just do D. Yeah, once they fix that, should be sitting first. Anyway, okay, so yeah, I think we can just sort these. Is that what I want to do? I think that's fine. That's fine. Okay, so that's what we're gonna do. Yeah, let's just do it. So in that case, are these 0 based or 1 based? These are 1 based. So let's subtract B, comma C, A, comma C. Okay, so sort them all. And now we're gonna have queries. So compiler, that's fine. And now we're gonna do. Well, really, I should just do this. Just let this be handled by. This should also be honestly be handled by that function. Alright, and now maybe this is an error. Okay. Yep, and now we're going to go iterate through x's. First of all, this is fine. Just the x. Oh, this needs to be N64 because it can be a lot. It's fine, okay. Cool. And then do make pair. I guess it's at most, it's at least 0, right? May 0. If it is also by the end, and it first equals name. If it equals that neighbor, then answer plus equals min Hit second, hit second. And I think that's it. I missed the new line at the end. 25, 20. 25, 20, 32, 20. And this is fast. D. Okay, I think they'll resolve it for me. Cool, and then we are saving everything. We're sorting, mapping, saving, iterating through the smaller list. Oh, that's not wrong. If it's directly, then just do 2, otherwise find it. If it's not the end, and we match the neighbor, add the min, save the answer, 64-bit. All right, let's do it. Let's do it. I might have to do this. Can't run in debug mode, it's too slow. This one is quite slow, actually. I think I'm still just going to do the full input download. Okay, cool. I was expecting because it's a square root. Let's just run it again just to make sure that I didn't mess it up. Really using my CPU here. Should be almost done. Cool. Second flight output, d.cc, submit. Cool. If this one bugs out too, that would be frustrating. Nice, got it, all right. Let's just double check, but cool, sitting in first. I should have 100 points. They had a bug on their end, and they said they'll handle this while I'm working on it. So yeah, I'll finish up here. I'll go through and talk about each of the problems. And let me just pull up what I've got here. So let's see. Let's just open C++ files. Cool. All right, let's start with problem 8. Cool. So problem A, you've got n parts, and you have 2 cases. You want each case to hold some of the parts. and each case can hold at most k parts. You know the style of each parts, and you only want to have at most one part of each style in each case. And determine if this is possible. That's all you got to do. Just print a yes or a no. In this case, because you can only have one style in each, if there's any style with 3 or more, then you can't do it. So that's the first thing we check here. So basically you read the input, count the frequencies of each style. If there's any style with more than 2, it's a no already. Otherwise, we have some styles that have 2 and some styles that have 1. And then the only constraint we have left is we need to make sure use at most k parts. And what we're going to do is basically the 2s obviously have to go 1 in each case, but the 1s we can split them up how we want. And we should split them as evenly as possible. And so basically, one of the cases is going to get the number of 1s divided by 2 floored. One of them is going to get that ceiling. So, for example, if 1s equals 7, it'll be 3 and 4, right? So the worst one will have the ceiling of 1s divided by 2, and so that's what we do here. 1s plus 1, 4 divided by 2, that gives you the ceiling. That plus 2s is going to be how many you have in the case with more, clock ports. And so as long as that is, at most k, you have a yes. If it's greater than k, you have a no. Cool, that's problem A. Problem B. Problem B, part 1, is definitely the simpler case. You have a grid and you want to fill it out with some number of trees. You want to make sure none of the trees are lonely, which means all the trees have to have at least 2 tree friends. 2 trees which are adjacent in the 4 directions. So, and you can have 3 or 4, but you need at least 2. You're given a sort of terrain, and you need to figure out if it's possible to add more trees or potentially not add any trees so that all the trees in it are happy. And some examples here. The key observation here is if either of the dimensions R or C is 1, then you're going to have somebody on the edge on the corner. That tree can never be happy. And so you're going to have a problem if you have any trees. For example, if you have a tree like this, it's like, well, this tree needs 2 neighbors. You add these 2. This tree needs 2 neighbors. You add this one. This tree needs 2 neighbors. You add this one. And then by the time you get to the end, the tree on the end cannot satisfy it. It's going to be lonely. So it's just going to be a no. So if R is 1 or C is 1, it's only possible if there are no trees. If there are any trees, it's impossible. Yeah, and then otherwise, all we need to do is, if there is a tree, we just fill out the whole grid. That's the easiest way to do this, because as long as R and C are both at least 2, every cell in a 2 by 2 or greater square has at least 2 neighbors. So if we just fill out everything, we're good. That's B1. B1 is definitely simpler. B2 is the same idea, but it's trickier because zipped output as well. Okay, I guess I'll send them that. What is it? Second friend output.zip. Second friend output.txt. Yeah, that is much smaller. Okay, I'll just send that as well. Let me just double check this. 1 friend. Yep, that is the same. Zipped output as well. Cool. Yeah, hopefully they can take care of that. It's a little bit inconvenient, but anyway, cool. So now we have the same grid and we have the same problem. the grid is bigger. It can now be up to 3,000 by 3,000. So there can be 9 million cells in this grid. And there can be rocks. What does that mean? That means you can't put a tree there. So same problem, you may have some trees, you may have some rocks, you need to fill it out, but you cannot put trees on the places where the rocks are. So you can't do this cute idea of filling out the whole grid anymore, because that might not work. You know, you might have something like this with a rock here, and if you put this tree is going to be lonely. So you would actually have to avoid putting that tree and put trees like this instead, or even like this. Both of those are fine. So this is definitely a much trickier problem than B1. Main idea here is that even though we have a grid, it's easier to think about the problem as just a general graph with nodes and edges. If we have, if we take our grid and we convert it to a graph, and of course the rocks are not actually nodes, so we just kind of remove the rocks from our graph, then we have a nice graph where the key idea is if somebody has only one neighbor, or even fewer than one neighbor, no neighbors, then we have to remove them. They cannot become a tree. And then so on and so forth, where, you know, for example, if you have a path like this, then you would have to remove this guy, cannot become a tree. This guy also cannot become a tree as a result. This guy also as a result cannot, and so on. And you keep going down. So you have this kind of peeling effect. And the way we can implement that here is just with a queue. It's like a kind of like a topological sort, but a little bit different in this case. But anyway, what I do is I just go through, I build the graph. So I have R times C nodes, which is potentially 9 million in this case. So it's a lot. Find everything that's not a rock, check all the neighbors. If the neighbor is in the grid and also not a rock, then we add an edge, calculate degrees. Everything with a degree of 1 or less, well, I guess 1 exactly. We just push into the queue and keep processing the queue for each neighbor. Decrement its degree. If you hit 1, you put it into the queue. And so this way it's that peeling effect that we were talking about. And then finally by the end, everything that has a degree less than 2 cannot be a tree. And so if we have a tree existing that was degree less than 2, then it's impossible. Otherwise it's possible. We just fill out everything with a degree of at least 2 to become a tree. And we print that out. So that's B2. Definitely a little bit more challenging than B1. But key idea is, you know, finding the degree 1 nodes and peeling them and moving on. All right, problem C. So I actually admit for problem C, I don't really understand why we have two problems, C1 and C2. I ended up just solving C2 directly. So I can talk about that. So basically, you're given, we have some context about Morse code. You're given these different code words for each letter, for example. And then the problem is if you take out the spaces, there are different ways to interpret the sequence. And so we want to set it up so that we want to build an encoding where there's no way to interpret it differently. And we're starting out with one code word, and we need to generate the other n-1 code words, so that there's no ambiguity in our encoding. And n is at most 100. The length of C1 is between 1 and 100, and the remaining characters, or the remaining code words, have to be at most length 10. So what I did here actually ended up being pretty simple. Basically, C1 is kind of its own thing. For C2 through Cn, I'm going to avoid having the same first character as C1. So if C1 starts with a dot, I'm going to have all of these start with a dash, and vice versa. And then I'm also going to have them all be the same length. I'm going to have them all be length 10. And then aside from the first letter, they're just all going to be different. And so I have 2 to the 9th options, which is 512 options, plenty of options, much more than 100. I guess I only need 99 technically. And yeah, that's basically the goal here. So if C, I guess the output on the sample is sort of insightful. Maybe we can even take it a step further and go to 10. Dot dash dot. Basically, we're going to start everything with a dash. Everything's going to be length 10. And then otherwise, we're just going to start using any combination that we haven't used before. So the way that I coded this, to keep it simple, is you just kind of take the number I, you write it in binary on these 9 characters. So this is going to be 0, 0, 0, 0, 0, and so on. This is 0, 0, 0, 0, down to a single 1. This is 1 and 0. It's in reverse, so it's a little tricky. But yeah, these are all just numbers written in binary, so they're all going to be different. And then once you have this language, you have this code word with all of these, it's always unambiguous. Oh, excuse me. It's always unambiguous because if the first letter is a dot, then you know it's this one, and you just read that. Otherwise, you read the next 10 characters, figure out exactly which one it is, and then move on to the next one. So there's no ambiguity here. That solves both subtasks. All right. And finally, we have problem D, second flight. So problem D, we have a bunch of flights. Flights go both in the morning and the evening in both directions. And we have a bunch of queries. Each query wants us to determine how many tourists can fly from airport X to airport Y that day. There's 2 ways to do that. You can fly directly from X to Y if there is a flight, which means you can do that in the morning or the evening. Or you can take a morning flight from X to Z and then take an evening flight from Z to Y. Those are your 2 options. And you want to know how many people can do that. We're also given, for each flight, how many people it can carry. So there's a pretty easy quadratic solution right off the bat. What we can do is, for each query X and Y, we just figure out, essentially we want to know, first of all, we take the direct flight path, see if there's a direct X to Y flight. If so, add 2 times that capacity. And then otherwise, we're just going to try every Z. If there's a flight from X to Z and a flight from Z to Y, then we can add that. The time complexity here is going to be n times q, which is too slow in this case because we don't want to do 200,000 squared operations. That's going to take quite a while, especially given how many test cases there are. So instead, what I ended up doing is there's a clever idea where you can, instead of looping over every Z, we know Z has to be a neighbor of X and it has to be a neighbor of Y. So instead of looping over every Z, we can just loop over Z's that are a neighbor of X and then check if Z is a neighbor of Y as well. So that helps us. The problem is that's not good enough because if every time we do a query, X is the busiest airport, it has a flight to everywhere else, that could still be n time. So the one optimization here is, well, we can loop over X's neighbors and check if they're neighbors of Y, or we can loop over Y's neighbors and check if they're neighbors of X. And given that we can pick either, well, we might as well pick the one with the fewer neighbors, right? But you can get unlucky. You can have X and Y both have a ton of neighbors. Right? The key idea, though, is that once you solve an XY query, you can save it and you don't have to solve it again. And if you think about it that way, then it actually turns out that the total amount of work you do with these 2 optimizations combined, first of all, saving the queries, and second of all, using the node between X and Y that have fewer neighbors. If you combine these 2 optimizations, you get a square root runtime on average per query. The reason for that is essentially you can imagine having a list of your degrees of all your nodes. Maybe it's 0, 0, 1, 1, 1, and let's sort it, right? 6, 10, 12, something like that, right? If you pick 2 nodes, for example, you pick the 3 and you pick the 12, the cost of the query is going to be the smaller of the 2 numbers. It's going to be the 3, right? And so even though this 12 is really big, you can't actually take a cost of 12 on a query because there's no nodes with higher degrees than it. And you can do some analysis here. There's probably something simple, but basically what you can show is that if my degree is d and I have k things, right, in this section I have k things that are greater than me, the idea there is that then because there are k things greater than me, d has to be at most, it's like n divided by k or so. Yeah, I think this is good enough to show. So basically, yeah, d is at most n over k roughly. I guess it's n over. We can actually we should make k include our current node. Yeah, so in this case, k is 4. So yeah, d is at most n over k. Maybe technically this is like a 2n or something like that because the sum of all the degrees is 2n. But anyway, the point is it's on the order of within a constant factor of n over k. And so basically, in the worst case, the top guy is n, the second highest is n over 2, n over 3, n over 4, and so on. But the thing is, the n has 0 possible queries where they're the smaller one. The n over 2 only has 1. The n over 3 has 2 possibilities, and so on. And so if you basically add up all of the worst possible queries, it looks something like this. And so we notice that the sum of all of these, because by the time you get to here, you have had square root n entries and square root n rows, and each of these products is less than n, right? This is less than n, this is less than n, this is less than n, and so on. This is technically this. All these is less than n. And there's only square root n rows, so the total sum is at most n times square root of n, right? And by the time we got to here, we've done on the order of n queries in total, because that would be the sum of 1 plus 2 plus 3 plus so on, all the way to here. And so that's why we get the square root. Okay, great. They created a submission for me. Nice. Bit of a slow scoreboard. Okay, cool. Officially sitting in first place. Pretty big time lead, actually, over second place. So, looking good. All right, still thinking about that proof. I think this is like a reasonably easy way to do it. There's probably a simpler way if I thought more about it. But I would like to grab some lunch. So anyway, that was it for Facebook Hacker Cup qualification round. That's it for me. Hope you enjoyed it. Hope you learned something from this kind of walkthrough. Yeah, if you're new to the channel, feel free to subscribe and check out my future videos. But thanks for tuning in, and I'll see you in the next one.